So let's start with our topic, that is phase changing material. So we can call it as PCM. So PCM has started to attract attention in order to improve the efficiency of the plants. So we can use PCM to improve the efficiency of plants. So because we can use PCM in thermal energy storage or thermal energy management. So we can use PCM for two purposes, that is thermal energy storage or for thermal energy management. So let's talk about what is PCM actually. So we can say PCM is a material that has significantly large value of phase change enthalpy. So basically, PCM is a material which has large value of phase change enthalpy. So due to this, it is able to store a lot of thermal energy and to release it if temperatures cool down. So basically, we exploit phase transition and the enthalpy associated with the phase transition. So basically, we exploit in PCM phase transition and the enthalpy associated with this phase transition. So let's imagine we want to exploit solid liquid phase transition, that is melting of the component. So if we start in liquid state, which is decreasing its temperature, that is releasing heat, and when we end up in fully solid state phase change material, so we can have the discharging cycle. So our PCM material will start increasing temperature and will start melting, and we will get liquid material. So I think in few seconds we will see with the help of with the help of the diagram what I'm talking about right now. So the idea is to have really small material which is able to store a high energy. So when we are able to store or release heat, we are actually having a material that is behaving as a thermal capacitor. So basically PCM behaves as a thermal capacitor. So when you are able to absorb or release heat, we are actually having a material which is behaving as a thermal capacitor. So we are able to maintain the temperature as constant as possible by storing and releasing the excess heat that we have in our system. So now I will draw one diagram so we can explain or we can understand it better. So let me draw in this fashion. Okay. So on x-axis we have time, and on y-axis we have temperature. And suppose our graph looks something like this. Okay, so okay, let me draw it first, and we are going to draw something like this. Okay, and again we are going to draw something like this. Okay, let me So we have two different ways to store heat. So we have sensible heat and latent heat. We have two different ways to store heat. First is sensible heat, and second is latent heat. So this is when we increase the temperature up to here. So we can call this as a sensible heat here, and this is the latent, and this is sensible. This is also sensible heat, latent heat, and sensible heat. So we can say this is I will come back to this point. So this is basically heating process, and this is cooling process. Now let's start. So let's start what is sensible heat and latent heat. Okay. So sensible heat is the heat which is stored simply because we raise the temperature. So this is the sensible heat because we are raising the temperature up to T or phase change. So this is called sensible heat. So we are providing energy to our system. So imagine to have a solid component which is little bit cooled, and we start to heat our phase change material. At the beginning of the heating, we store sensible heat in this form. So then we reach a temperature in which we have phase transition, basically this temperature. So at this point, which we have phase transition, we are providing heat to our system by raising the temperature, and this heat is stored inside our material because of phase transition. So, and if we continue to raise the temperature, that is, we continue to provide energy to the system, we can continue to store heat as a sensible heat. So latent heat is basically obtained from the phase transition. So the heat or the energy which is stored in the system due to the phase transition is called the latent heat. So, and okay, so sensible heat is basically related to sensible heat is basically related to specific heat of our material and the difference of temperature. So we can write the whole expression for our in this diagram which we have shown. So we can write the expression as Q heating is equal to we are going to integrate from T initial temperature to the phase transition temperature, that is CPS dt. That is CPS is the specific heat of our material, and it is the difference of temperature. So this is basically we can say this is specific heat of solid. It is specific heat of solid here. Now we can add here the latent heat. So we can write latent heat as mxm del hm. Del hm is basically the enthalpy of our system. So so this is our latent heat. Latent heat plus again sensible heat when solid gets converted like due to liquid one. So due to cooling system. So let me write it from TPC to T final, because this is the T final. Sorry, this is the T final. So from phase transition to again T final, we are again providing sensible heat. So we can write again MCP L dt. Okay, so this is basically main expression for our phase change material here. Now, if we have a phase transition instead, we have high enthalpy of melting or phase change. So you should keep this in mind. Now let's see the concept of phase changing material with the help of an example. Um, so let's see an application for it. So I will draw. So let's imagine there is a building with a metal at the rooftop. So I will draw something like this. So this is our building basically. So this is the metallic metallic rooftop, and draw something like this. Okay, so this is our sun basically. And let it divide by this. It is hot and here is cold. Okay, and this is the overheating here. Overheating. And let's see other case scenario where we have during night time. So during night time, sorry, my drawing is not that perfect. Okay, so this is during night time, we have heat loss. Okay, so let's understand the concept. So during the day, we have heating of the rooftop and we have lot of heat transferred to the room. So our room will heat up a lot during the day. But during the night, if the temperature drops quite a lot, we will have a lot of heat dissipation and we have consistent change of temperature in the room from day to night. So now let's say we want to insulate our rooftop with foam. Insulate our rooftop with a foam filled with phase changing material. So during the day, heating is enough to allow the activation of PCM. So during the daytime, we have activation of PCM due to heating. So our PCM will start to store energy and the overall increase in temperature in the room will be lower during the daytime. And now let's focus on during the night time. So during the night, we had drop in temperature which results in solidification. So during the night time, we have solidification of our PCM material due to the drop in temperature. So where heat is released due to the endothermic transformation and the heat is released to environment. So we release it both towards outside and inside of our building. So we will have a high temperature in our room in comparison to the room without PCM. So from practical point of view, this is used in track. Let me draw one graph to make you understand the our concept. Okay, yeah. So during daytime, there is a heat storage. So this is our time and this is our temperature on y-axis. So without PCM material, we have graph something like this. Okay, choose this. Okay. So this is our graph without PCM material. Now, if I draw the graph with PCM material, it looks something like this. So we have firstly rising temperature, then we have phase transition. Again, we have rising temperature. So basically, this is sensible heat, this is latent heat, and this is again sensible heat. So this is basically with PCM material, with PCM. So basically, this represents the heat storage. So basically, this represents the heat storage process. Heat storage. Now let's focus on the night time, which is heat release, which results in heat release. Okay, let me draw something like this. So this is our, on x-axis we have time, on y-axis we have temperature, and due to the heat release our graph will look something like, will look something like this. Two. Okay, so this is our heat release process. This is without PCM. So this is without PCM. Now with PCM we can get the graph something like this. So okay, then we have phase transition, and again we have here. So this is latent heat, then here is this is sensible heat, this is latent heat, and again we have sensible heat here. So we have here difference in temperature here, delta T, and also here the difference in temperature, delta T. So if we use latent heat or specific heat, we can change the quite lot of energy that we can store inside our material. So if the material can just store sensible heat, we will need a material with really high melting temperature. So if our material just absorbs sensible heat, if material absorbs only sensible heat, we will need a material. So we will need a material with really high melting temperature. Example of these materials are water, stone, wood, and plastic. Examples are water, stone, wood, and plastics. So if we move to the PCM, which can store only latent heat, so if material absorbs only latent heat, we see that amount of heat storage capacity is increased to 5 times. Amount of heat storage capacity is increased to 5 times. So simply by adding a phase transition in the temperature of interest, we are able to store much more heat than we can do by the sensible heat. So in physical process, we can store the energy by sensible heat and latent heat. So the transition which involves gas is not desirable as they can cause increase in volume and unwanted reaction. So solid transition is one of the most desired, as we need not to confine our PCM material. So solid transition is most desired as we need not to confine our PCM material. Now let's talk about the PCM properties of okay. So let's talk about the PCM properties right now. So first thing we need to know, if we want to have solid liquid transformation, that is the melting temperature. So melting temperature of PCM should be in desired range for our application. So first is melting temperature of our PCM material should be in desired range. Second thing we need to consider is the enthalpy of phase transition. So second thing we need to consider is the enthalpy of phase transition. So in this case, we can have melting and latent heat associated with the melting. So we have latent heat per unit volume and per unit mass. So basically our latent heat is expressed in, latent heat can be expressed in per unit volume or per unit mass or per unit mass. And if we want to reduce the weight of our component, we'll go by unit mass. So the third property we want is high thermal conductivity. High thermal conductivity. So as we want temperature to be homogeneous as possible of our component, so we need long-term stability in terms of thermal response. So we have a material that for each cycle is behaving as same way in long term, and also we want structural stability. Structural stability. So as liquid is stored in confinement box and our box needs to be stable to bear this type of transitions, and we need a small change in volume during phase transformation, and we need a small change in volume during the phase transition. Okay. Because if we have phase transition, our volume is going to increase, and we don't want stress generation in our confinement box. So if we want high specific heat, because if we want to go to high temperature, and if we are able to store heat by both sensible heat and latent heat, and we are getting an advantage as we can store large amount of heat due to this type of process. So we don't want to increase our temperature too much, as PCM will always in liquid state. Okay, I think I should stop now because it's getting lengthy. So we can discuss the further about the PCM in the next lecture, I guess. So for now, thank you.